The switch statement is a standard tool in programming, used to filter a single variable down into one of many possible outcomes. Developers rely on it because it offers a clean, highly readable syntax for writing multi-way branches. But for the compiler tasked with parsing that code, this structure introduces a significant mechanical hurdle. The compiler's immediate objective is to translate the source code into an intermediate representation. Specifically, it must generate 3 address code, a precise format where every instruction executes a single basic operation. It must achieve this under a strict mechanical limitation. Standard compilers operate on a one-pass architecture. In a one-pass system, the parser reads the abstract syntax tree moving strictly from top to bottom. It emits intermediate code sequentially and has no ability to look backward to modify what it has already written. This forces the parser to take a multi-branched, non-linear concept and flatten it into a strictly linear sequence in real time. Translating a switch statement is a specialized forward routing problem. It requires a specific structural workaround to ensure the execution path reaches the correct statement block in a single pass. If we attempt a naive, direct translation, we would map the block sequentially, placing the first evaluation test at the very top of our intermediate code. But the moment the parser tries to emit that first test instruction, the process breaks. The test instruction needs a target address. It must tell the program where to jump if the condition is met. At this stage in the parse, the labels for the destination statements have not been generated yet. The compiler cannot simply skip ahead in the source file, scan the upcoming cases, and fill in the blanks retroactively. It also lacks the ability to pre-calculate the exact memory size of each statement block before physically translating them. The target destinations are unknown. Placing evaluation tests at the top of the block violates the rules of a one-pass system, meaning the physical layout of the code must be inverted. To see how the compiler solves this, we can step through the translation of a new switch block, strictly from the top down. The parser's first action is to handle the selector expression. It evaluates this expression and assigns the result to a newly generated temporary variable, t. Immediately after this evaluation, the parser hits the opening bracket of the switch block. Knowing it cannot process the routing logic yet, the compiler emits a single unconditional jump instruction. Go to test. At this exact moment, the test label does not exist anywhere in the intermediate code. This jump operates as a forward-declared placeholder. It aims the execution flow at an address that will be defined later in the sequence. This single instruction defers the evaluation phase entirely, buying the parser the time it needs to translate the body of the block. Moving inside the block, the parser reads the first condition. It generates a new label, L1, and directly emits the intermediate code for that statement. To match the high-level behavior of a switch statement, the execution path must be forced to exit the block rather than falling through to the next case. When the parser encounters the high-level break command, it translates it into another unconditional jump, pointing to the eventual end of the structure. To organize the routing logic for later, the compiler relies on a short-term memory structure, the queue. The compiler takes the specific condition required to trigger the current case and pairs it with the physical label it just generated. This value label pair is pushed directly into the queue for temporary storage. The parser then continues downward, repeating this exact sequence of actions for every subsequent case. As it reads, the intermediate code simply stacks these independent statement blocks one after another. At this stage, they lack any logic connecting them together. When it reaches the default case, the parser assigns it a unique label, requiring no specific trigger value. By storing the value label pairs in a separate memory queue, the compiler successfully decouples the evaluation data from the physical execution blocks. The parser eventually reaches the final closing brace of the switch block. It immediately generates the test label at the very bottom of the intermediate sequence. All statement blocks have been physically translated. All target labels now exist. The parser is equipped to build the multi-way branch. It initiates the unrolling phase, pulling the saved data from the queue. Each pair is translated into a 3-address test instruction. If the temporary variable t matches the case value, the program jumps to the corresponding label. This entire cluster of routing logic is placed safely beneath the statement blocks, satisfying the constraints of the one-pass system. A final jump to the default label is appended, followed by the next label, which marks the exit of the entire structure. The resulting physical layout of the code is completely inverted. The evaluation tests are written last, executing only after all required variables and labels are strictly defined. Deferring the tests to the bottom of the block naturally initiates the next major phase of compilation, code optimization. Gathering all the case values in the queue empowers the final code generator to analyze the complete dataset mathematically before it emits the machine code. The compiler must choose the most efficient way to implement the n-way branch in physical memory. If the switch contains a small number of cases, typically under 10, the compiler relies on a linear chain of conditional jumps. If case values are tightly grouped within a specific range, it builds a jump table, a contiguous bucket array in memory. Here, the case value acts directly as an offset address, allowing the branch operation to execute in constant time. Finally, if case values are large but sparsely distributed, the compiler generates a hash table, routing the sparse inputs into packed memory. The one-pass workaround, deferring the tests via the queue, is the exact structural feature that exposes the entire dataset, enabling these advanced memory optimizations. Zooming out to view the completed intermediate representation, the final execution architecture is clear. This overlays a control flow graph onto the generated code, mapping the true execution loop. At runtime, the program evaluates the selector expression, jumps down past the statements to the test block, jumps back up to the specific target body, and finally exits. The programmer writes a linear, easily readable list of options. The compiled machine code executes an erratic, vertical sequence of jumps. The architecture of intermediate representation is shaped entirely by the functional limits of the compiler itself. To translate sequentially, the code must be inverted, yielding an execution path optimized for speed rather than human readability.